right, our next topic is stereochemistry. And stereochemistry comes from the idea that this is stereos, which means three-dimensional space. So essentially, in this chapter, in this topic, we are going to consider what are the repercussions of when molecules have groups pointing in a certain direction. Now, when does it become important? How does it become important? In order to understand that, I would like to tell you a story. Back in 1950s or so, in Germany, there was a drug that was given to patients by the name of thalidomide. Thalidomide. And it was given essentially to treat morning sickness in pregnant women. What was found essentially 6 months later was that the children that were born to the babies that were born to these women had developed birth defects. So sometimes it was an issue with development of limbs. Sometimes it was an issue with the brain development. They were essentially born with birth defects to the point that some of them may not even make it. So it was a pretty grim situation. An entire generation of about 10,000 babies went through that. And it was, of course, researched, and it was found that all of those were linked to this one drug which was given for morning sickness. When the structure of that was deciphered, and when the structure of as to what else is happening, what was found was that the structure, if you compare the structure of thalidomide, which contains essentially two molecules, so we have a CO, C double bond O, and you have a solid line on this one, NH and NH. And if I draw the other one, maybe I'll draw that in red. It's a very similar looking structure, but N is on the dashed line. So the only difference between the two is that in the black case, you have your nitrogen, and this entire thalidomide, by the way, sometimes it's spelled without the pH, just starting at T, that is pointing up, and in the other case, it was pointing down. And what was found was that while one of these molecules was engaging in your treatment of the morning sickness, the other was actually causing the birth defect in the babies. And so essentially that was a problem point. Turns out that thalidomide is actually treated or used in the cure for certain types of cancers as well. And it is the R form, which we'll talk about in this chapter as to what that R means. But it is it is a clinically used drug. But back in the day, they did not know the difference between R and S form, so it was just given as a mixture. So it was kind of like 50% R, which is the bioactive form, and 50% S, which is the form you do not want, which is what was causing the trouble. So before we get into that, let's first lay the foundation of what is asymmetry, asymmetric center. What do we mean by what is also called as chirality, or the property of handedness? Now, what I want you to do, pause the video for now and take a moment to look at your hands, palms facing up, okay? And imagine if there is an imaginary plane which can serve as a mirror. So basically you have your palms facing up. This is your hand. You have your thumb. You have your index finger, middle finger, ring finger, little finger. I don't draw very well. And we are going to draw out the other hand. I have over here the thumb, the index finger, the other hand. Okay? They didn't come out exactly right, but this is what I want you to imagine. I want you to imagine the mirror plane in between. Mirror plane. Hopefully you can see that the left hand is the mirror image of the right hand, right? And so whenever you have a property like that, that one half is a mirror image of the other, and there is no plane of symmetry in that mirror image, we say that there is a property of handedness. What I want you to do now is put your hand, so take this the way it is, and put that on top of your right hand, okay? So you're going to see kind of like an inverted turtle, or you can do that with your on the dorsal side of your hands as well. So palms facing down. If you put your left hand on top of your right hand, you should end up with a turtle. You should end up with a turtle. Right? I do not want you to fold over to say namaste. That will become superimposable. I want you to actually lift one on and put it on top of the other. And that will be the asymmetric scenario that we are talking about, where you are going to end up with a non-superimposable mirror images. So if you look at your hands, you basically had no plane of symmetry. That means you cannot divide your hand into two equal halves. So no plane of symmetry was found. And if you look at the mirror image of your hand, you can actually lift one over the other, put it on top of the other, and that will give you non-superimposable mirror images. Mirror images. And when you are able to achieve that, that is what is called as the property of handedness. In case of organic molecules, this can only be achieved if you have sp3 hybridized carbon atoms. And you have the kind of sp3 hybrid. So what you need is an sp3 hybridized carbon atom, which has four different groups on it. What that means is that you have four different carbon-carbon single bonds. Okay. Now, the SIP rules, which are Kahn and Gold pre-log, they suggest that if you have an sp2 hybridized, for example, in which case we did the E and the Z, remember? And so when you're looking at your priority groups, when you're comparing the groups, the moment it's something sp2 hybridized, it would mean that you're going to be counting it twice. And so what you would have here and what you would have here is going to be exactly the same, which is why things like sp2 or sp would not work. You need all single bonds, and you need four different groups that must be present. The other requirement, which I already talked about, was that there should not be a plane of symmetry or a line of symmetry going through the molecule. So that's another requirement for something to be chiral. And lastly, we want non-superimposable mirror images. So three requirements for something to have a chiral center are You must have sp3 hybridized carbon atom with 4 different groups. There should be no plane of symmetry through the molecule. You should have non-superimposable mirror images. So recall the turtle. You don't want namaste. You don't want folding over of your hands. You want actually to lift the molecule and put it on top of the other. We'll take a look at each of these as to what they mean. So the reason why you want, like I told you in the beginning, the reason why you want to have a handle on this stereochemistry is because in biological systems, certain molecules are going to fit in the pocket and its mirror image may or may not fit the exact way. And hence, this handedness or the property of handedness, the chirality, is an important property in both organic and biochemistry. So over here, I'm showing you the meaning of non-superimposable. Non-superimposable. If you had a carbon which had perhaps all 4 bonds going to hydrogen, and you took a mirror image of that, notice that if I were to lift this and put it on top of the other, there's going to be a complete match. You're going to have 4 carbon-hydrogen bonds matching right on top of each other. That would become superimposable. Superimposable. That is not what we are seeking for chirality. You want to make sure that these groups are different. So make a note of what we have here. This is lactic acid, and what you're looking at is the carbon in the middle. You have a hydrogen on top. You have a COOH on the side. We have, of course, the CH3 and OH. If you look at the mirror image of that, then the 2 groups are flipped. And if I wanted to really draw that out, I could show this like an OH, H. You can draw it differentially too. CH3, and at the back I have COOH. Let's perhaps make the mirror. So I have H on top, OH on the right side. I have COOH, and I have CH3. Now I want you to hold this and lift on top. This COOH is going to fall right on top of the OH. This OH is going to fall right on top of the COOH. The methyls would match, the hydrogens would match, but there will be a mismatch between the OH and the COOH, which is why you would say that these are non-superimposable. So in order for it to be non-superimposable, you must have 4 different groups. If they are the same, I just showed you, you can find positions on a one-on-one basis such that it will end up being superimposable. But what you have here, in case of lactic acid, you have complete non-superimposable mirror images. Sound good? All right, let's go for it. So that's what I'm saying here. I'm seeking 4 different substituents which are going to end up with non-superimposable mirror images, and that's what we call enantiomers. All right. Now, this slide actually takes you through each of those. So if you, for example, look at the CH3X, CH2XY, those are the ones in which your molecule and its mirror image are basically identical, and so they are not handed. On the other hand, if you look at the last one in which all 4 groups are different and you look at its mirror image and actually lift that mirror image and put it on top of the molecule, the blue is going to go on top of green, the green is going to go on top of blue, and that is going to cause essentially a mismatch. That means that it's not going to be identical to the mirror image. Since you can't superimpose, you would say that they are not the same, and hence we use the word enantiomer to describe that. Enantio in Greek means opposite. And so enantiomers are relative to each other as somewhat of a right hand and a left hand aspect of the molecule. And so you would say that a molecule is chiral, or it has the property of handedness, if it does not have a plane of symmetry that divides the molecule into two equal halves, if it has that chirality center that I have been talking about, which is the sp3 hybridized carbon center, 4 different groups on it, and then you would use the word chiral to describe that. And the property will be chirality. So in here, I'm showing you, essentially, you can use materials around you. So for example, look at an Erlenmeyer flask. You can actually divide this Erlenmeyer flask right in the middle. And so it gives you 2 equal halves. So there is a mirror plane going through the molecule, which makes this first one an achiral object. On the other hand, if you look at your hand, you essentially cannot divide the hand into 2 equal halves. Those are not symmetric. And so you would use the word chiral to describe this. So again, understand, recognize, realize that a molecule is not chiral if it has a plane of symmetry. So you must make sure that there is no plane of symmetry or a line of symmetry which cuts through the middle of the molecule in a way that one half ends up being the image of the other. All right. So let's take a look at which of the molecules does not have a plane of symmetry. Notice the first one, there is a plane of symmetry going right from the middle. If you look at the last one, there is a plane of symmetry going through the molecule. Always try to draw out the chair the way it exists. So if you were to, let's try to get a better chair. So if you were to actually put down you have your methyl, so you have the 3 H's, right? You have your isopropyl group here, which has a hydrogen. So you can include a plane with a middle hydrogen and this hydrogen, which is going to divide both of them, the 2 CH2s on each side, the 2 methyls on each side, the 2 CH2s on each side, the 2 hydrogens on each side. So basically, one might say that if you were to view in this direction, you're going to see essentially you would see the crowning, if I would be able to draw that right. Those are your CH2s. This is crowning up. This is crowning down. And so you have over here a hydrogen on each side. This hydrogen is in the plane, right? This hydrogen is in the plane, and you have 2 methyl groups. So we are saying that there is a plane that's dividing essentially the molecule into 2 equal halves, methyl and methyl. And so this 2 essentially is dividing right in the middle. And if you look at the one that you have over here, if you try to draw the line, the H finds a Cl, this H finds a Cl. The answer to this is item number 2. So again, if you were seeking a chirality center, first things first, must be sp3 hybridized, must have 4 different groups. That's a really important point. And you would want no plane of symmetry in that molecule. Only then would you say that it contains a chirality center. Sometimes chirality center is also called as stereogenic center. Some people call it asymmetric center. Sometimes it's also called as stereochemical center. Either way, if you had to find it, you would look for the sp3 hybridized carbon with 4 different groups, and you would put an asterisk to show the presence of one. And if you have at least one, you would say that there is chirality in the molecule. Now, once you have determined the number of chirality centers, 2 to the power of n, where n is the number of the chirality centers, gives you the number of enantiomers, the number of optical isomers that might be present for that particular compound. What that means is, for example, in this case, you have only one chirality center. That means only 2 isomers are possible for this particular compound. All right, so this slide basically shows you the difference between 2 molecules. We have methyl cyclohexane and methyl cyclohexanone. We are calling methyl cyclohexane a symmetric molecule, which is achiral, as compared to the methyl cyclohexanone, which is chiral. And the reason why we are saying that is because this molecule can be divided. Notice this is exactly what I was trying to do previously. The methyl is a part of that symmetry plane that we were discussing previously. And so you would be able to divide the molecule into 2 equal halves. On the other hand, if you try to do the same thing over here, one side starts to get the C double bond O and hence makes the position here, which contains a methyl, contains a hydrogen, contains a CH2, and a carbon containing a C double bond O as 4 different groups. So if I were to label that, I would say, here is my chirality center. So the question this hour is, which of the following has a chirality center? I'm looking for all sp3. They are sp3. I'm looking for 4 different groups. And so you have that in number 4. Notice we are putting down 1, 2, and 3 in a 3-dimensional space. That means that there is a solid bond, there is a dash bond, but that does not mean that there is chirality. A lot of times students just look for, oh, it's written on a solid and a dash. I could put methane in a solid and a dash, all right? So keep that in mind, that you must make sure that you have a certain that the groups that are present are 4 different groups. All right. Let's take a look at maybe another molecule where I can just kind of go over what we have learned so far and be able to tell which is a chiral center and which one is not. So as daunting as it might look, there's some bonds that you can just right off the bat, you can remove, that they are not going to engage in any form of chirality. So if you have sp2 out of the window, sp2 out of the window, sp2 out of the window. If you look at the carbon atom over here and you consider the groups, you have the groups extending in this direction and in this direction, which are exactly the same if you go atom by atom. And so that also is not going to contribute to any chirality. Anything which is a CH2 would mean that you have 2 hydrogens, right? So even if your 2 other groups are different, you have these 2 which are identical. So that is not chiral then. So anything which is CH2 is not chiral as well. So I'm going to mark those away. This is a CH3 out of the picture. This is CH2 and that's CH3. So everything that I marked red essentially is not chiral. Let's see if things that I have now are chiral or not. I should probably mark this CH3 as achiral as well. So let's take a look at each of the other ones. Here you have a hydrogen, you have this big bulky thing, you have a methyl, and you have an ethyl. Looks like that is going to be chiral. Let's take a look at the next one. I have a carbon, it's going to a CH2, it's going to the big bulky thing. It has a hydrogen, of course, and then it has the sec-butyl group. So sounds like we do have that as a chirality center. You can take a look at the next one over. You have a CH going, you have one going towards the seg-butyl. You have another one going on the other side. The fourth one is a hydrogen. Looks like that's going to be chirality center as well. Likewise, if you look at the next one over, one goes to the methyl too quickly. The other goes to the double bonds. The third goes to the seg-butyl. And you have hydrogen. Sounds like that will be chiral as well. For the same reasons, if you look at this one, comparing our bonds, that will be chiral, and so will be this. So we have overall 1, 2, 3, 4, 5, 6. Oh, I forgot this one. We have a hydrogen, we have a methyl, we have this going to a seg-butyl. That's chiral as well. So we were able to find 7 chirality centers. That means 2 to the power of 7. That will be 128 molecules, which will serve as optical isomers. All right, let's consider now how would you be able to identify or recognize chirality or optical activity in a lab. So far what we have talked about is if we are able to look for the plane polarized light, if the structure is drawn. We have talked about the enantiomers. Essentially, we have some information on how the molecule is drawn. But if you walk into the lab and I give you a test tube with a colorless liquid and I ask you go figure, what would you do? This test was, or this study was first done, it was first investigated by a French physicist. His name was Jean-Baptiste Biot, who basically looked at the plane polarized light. What he did was that he took the beam of ordinary light consisting of electromagnetic waves that oscillated in an infinite number of planes. So basically, he started with a source of light. You could use tungsten filament. Light coming out of it is going to move in all possible directions. So we'll have front and back, up and down, etc. So light waves are oscillating in all possible directions. He allowed it to move through a polarizer. A polarizer is like an anti-glare glass, and so you're going to allow the light to pass through this polarizer. So what that would do is it would allow the light waves to just now move in a single plane. So they're going to perhaps be up and down, and that's it. That's what you're going to see. And then he called this light plane polarized light. And then he allowed that to pass through your analyte. And he made his observations at the end of where he was studying this. And what he saw essentially was that when a beam of plane polarized light, which means when a beam having passed through the polarizer, when that hits something which is optically active, essentially those optically active organic molecules, and he studied things like sugar and camphor, these had the ability to rotate the plane of that polarization through an angle. And he found that not all molecules had the ability to exhibit this property, and so the ones that did, he called them optically active. This device that is able to do that in modern times is called as a polarimeter. So polarimeter, as the word suggests, meter is to measure, and polary is to measure your optical activity. So optical activity is measured in terms of what is called as alpha, which is referred to as optical rotation. So let's take a look at the setup one more time. The light is passing through your plane polarizer. So there's two sets essentially. You have your light. It's passing through the polarizer. Once it becomes only moving in one single direction, it is allowed to move through the analyte, and that is what then is going to be studied. And so what you study is alpha, and what was found was that some molecules were able to turn this plane by some extent. So I want you to be reminded of what you saw. This is similar to what you would see in a refractometer. In a refractometer, we started with what? A region of darkness. You had the cross section, right? And so what you would see in a polarimeter when you look through that eyepiece would be something like that. And in the analyzer, you essentially, in order to get the same extent of darkness, you would have to turn that dial by a certain amount. And you're basically measuring that angle. What is that new angle is what they are measuring. So essentially, when in the analyzer compartment, they put down an optically active organic molecule in that tube, and light was passed through that. Then you had to rotate the analyzer until the light was able to pass through it, and you got this new plane of polarization, which basically told us to what extent that rotation had taken place. And this is exactly what you're seeing. Notice how in the beginning, it starts to rotate just a tad bit and then bends all the way that now it has a different plane altogether. So initially it was moving in this direction. Now it is moving in this direction. Whatever is that angle is what is going to be measured by the dial. And hence you would be able to make a call on what that value might be. So this value that is detected is called as alpha. That is called as optical rotation. And it obviously depended on the number of molecules that are present in that sample. That means it was dependent on the concentration. It was also dependent on the length of the tube. That means more is the number of the molecules in there, greater will be that alpha. And the two can be tied together, what is called as a specific rotation, which is measured at a specific temperature given as the superscript on that square bracket, and given as alpha, the optical rotation, divided by the concentration times the length of the polarimeter tube. So your alpha is measured in degrees. Your L is the path length, so that's your tube length, path length. So that's measured in decimeter. And the concentration C is given in grams per milliliter or grams per centimeter cube. And it's done so that you have a handle on your comparing apples to apples. Your measurements in one part of the world are comparable to the measurements in another part of the world. A lot of times you would see this written down with a subscript of D, which is essentially for the so-called sodium D line, which is the yellow light which is emitted by the common street lamps which contain sodium in there. So yeah, that's the setup for the polarimeter. Now, as a result of this polarization, you can have this turning of the light to go in a clockwise direction, in which case you would call your molecule dextrorotatory, or D, or if it goes in the reverse direction, you would use the word levorotatory, or L. So dextrorotatory would mean that you would give it a positive sign for the alpha. Levorotatory would mean that you would give it a negative sign. So just those little ideas, putting that in place before we go forward. So to give you a flavor of this, we talked about lactic acid previously, which contains a chiral center. So you have on the same carbon, you have an OH, you have a CH3, maybe that's on the solid line, and we have a COOH, and we have a hydrogen. So let's say this is my first molecule, and then I will have a mirror image of that as well. So that's where the hydrogen would be. This is where the OH would be. This is where the CH3 is, and that's the COOH, right? So your alpha here, let's say that comes out to be plus 3.82. Then for its mirror image, the alpha is going to be minus 3.82. Now, the temperature that I was talking about, that sometimes is written out basically because the concentration is dependent on volume, and the volume is dependent on the temperature, right? That as the temperature increases, the volume is going to increase as well. So the concentration is going to change. So it's a good idea to mention the room temperature for that measurement that you are making. So one could say that in this particular case, your units of specific rotation are going to be, since you're measuring that as degree. So that's alpha divided by concentration times your path length. You would say that that is alpha, which is measured in degree, or you can say DEG. Concentration was gram per centimeter cube, right? And this is in dm, and that is about 10 centimeters. So if you wanted to get rid of the decimeter, then you will have to have the factor of that 10 to be put in place. Let's do a quick calculation. They have given you the value of, so this is the structure of an alkaloid. Called cocaine. And it has an alpha of negative 16. The specific rotation is negative 16. So 1.20 grams of the sample was dissolved in 7.50 grams of chloroform. So that's my solvent. And it was placed in the tube, which has a path length of 5 centimeters. Okay. What is the observed rotation? So observed rotation meaning alpha. So they have given you that alpha D is negative 16. And we know that that is equal to alpha divided by concentration times path length. And so you basically plug and chug, right? 5 centimeters. If you divide that by 10, that will give you 0.500 decimeters. And so your length is 0.500 decimeters. Concentration is 1.20 grams divided by 7.50. And that number comes out to be 0.16. And plug and chug. So your alpha comes out to be negative 16 times 0.500 times 0.160, giving you negative 1.3. So if this is a negative number, do you think this molecule, the way it's drawn, do you think this is dextrorotatory? Do you think this is D or L? And why do you say so? That's right. If you're thinking that it is L, then yes, you are correct, because it is a negative value that you got. Before even Biot's work was done, Louis Pasteur was actually the first one who had discovered the sodium ammonium salts of tartaric acid, which crystallized into their right-handed and left-handed forms. And this is a very a distinct but really rare behavior, that the crystals essentially, the two kinds of crystals that were obtained, they were non-superimposable mirror images. And so he worked carefully with essentially tweezers, and he was able to separate out the crystals into two piles, one that looked more in the right-handed format, and the other which looked more left-handed crystals. And so he was able to essentially start from the original sample and get approximately 50-50 of the right and the left. And so he was able to find how the original mixture, which was optically inactive, and now when you sorted it into the piles, you actually achieved optical activity. So that was sort of the first reference that if you have enantiomers, which are going to have two different versions of the same molecule, the specific rotations will have equal magnitude, but they will be opposite in sign. So one thing to sort of take forth, going back to the example of cocaine that you did, if you, for the given molecule, you find that alpha is negative 1.2, whatever, then for the enantiomer, that value will be a positive value for the same concentration and the same path length. So if your original molecule has a negative sign, its mirror image will have a positive sign. All right, so let's take a look at looking at specific configuration and assigning what are called as the absolute configuration. So this has got to do, we've discussed now in chirality around us. We have talked about how we would be able to look for it in the lab. But how do you distinguish between the enantiomers and the way they are drawn, and what do we learn from it? As you get really complicated structures, this idea of assigning absolute configuration comes in extremely handy, because you would be able to look at the configuration for each and every stereochemical center. Remember, I showed you one in which there was 7, and I said that it would have the ability to give you 128 isomers, because essentially which bond is towards you and which bond is away from you in those 7 configurations can be, those are mutually exclusive events, so they can be different. And so the question is, what is the process? How do we go about it? So many words, but I want to take a moment to just kind of highlight the rules and just remind you of the rules, and straight away jump into some examples so we can practice that along. The first rule is according to the SIP rules, the Kahn and Gold pre-log. This is similar to the E and Z that we did back when we talked about alkenes. So you would be looking at the priority order, and you would assign priority on the basis of the atomic number. So atomic number is what you are going to look at. And if there are 2 isotopes, let's say, then you may be able to use the atomic mass to differentiate between them. But the first thing to look for is the atomic number. That's step 1. So let's write that. Step 1, assign priority on the basis of atomic number. Step number 2, you have to keep the least priority group away from you, and then move the 3 groups from 1 to 2 to 3 as if they were a part of a steering wheel. And if you're turning the wheel, are they moving in a clockwise direction or in an anti-clockwise direction? If they move clockwise, we will call it R for rectus in Latin, or right. And if it is moving anti-clockwise, that is left, sinister, hence we will call it S. So R and S will be assigned onto the 1, 2, and 3 priority as to which direction they are turning. If a decision cannot be made while assigning the priority, and you do have like a double bond or the same atom, then you go to the next available atom till you find a difference. And if there is a multiple bond, like I said, then multiple bonded atoms are equivalent to the same number of singly bonded atoms. What that means is if you had a C double bond OH, that is similar to saying that you have 3 oxygens on this. Okay, so this is what I was talking about. So you have, once you have assigned the priority, you would want to view the molecule in a direction such that the least priority is away from you. And so in going from 1 to 2 to 3, looks like we are moving in a clockwise direction. On the left hand side, notice the similarity to a steering wheel. I'm calling it an R. On the other hand, in going from 1 to 2 to 3, I have to turn in an anti-clockwise manner, and that will be my S configuration. I'm going to go over molecules so you can see as to what needs to be turned. So again, rules. Let's take a look at each of these. So in this case, the priority order is already given, but if you were to compare, let's quickly do that. Nitrogen is going to get the highest priority if you compare. This is your chirality center, right? So nitrogen is going to get the first priority. Hydrogen is going to get the last priority because that has the least atomic number. Now, if you compare your carboxylic acid and the methyl group, the carboxylic acid is the one that is going to receive the second priority because it contains 2 oxygens that are next to it. Over here, I have only a carbon which is connected to 3 hydrogens. So if you were to compare the hydrogens versus carbon with single bonds to oxygen, you would say that that particular group receives a higher number, and for that reason, you are going to give that a higher priority. The point to make here is that when you look at this molecule from a direction such that the least priority group is away from you, you would see NH2 on the right-hand side, CH3 on the left-hand side, and COOH on top. This is 1, that's 2, that's 3. That means it's in going from 1 to 2 to 3, you are moving in an anti-clockwise manner. This must be S. Does that sound good? All right, cool. Now, you can view this because sometimes some people have difficulties viewing them. And so I'm going to go through some tricks also to show you, share with you some tricks so that you can make it easier for yourself. So let's first go ahead, go through the 3 molecules and see if we would be able to get there in a somewhat easier manner, get the same configuration or not. So I have here another molecule. The chirality center has been shown. That's the chirality center. And that's where we want to find out. If you look at the priority, my Cl has the highest priority, followed by my CH2 on this side because that's connected to a Cl, followed by my CH2 at the back, followed by my hydrogen, which is the least priority now, and that is pointing upwards. Now, in order to view this, I will have to kind of bend down, and I will have to view the molecule from the bottom. And if you do so my eye is essentially here. So if you do that, then you are seeing Cl on top you're going to see the CHCl, the second priority. On the left-hand side, you're going to see the CH2 on the right-hand side. So in going from 1 to 2 to 3, looks like I'm going anticlockwise. This must be S as well. Now, I don't know about you, but I find it pretty difficult to kind of sit under the molecule and try to visualize that. You can do it, but my neck kind of hurts. So another way that we have devised to do this is to go through the priority order. That remains the same. And then what I would do is I would look at, in going from 1 to 2 to 3, looks like I'm going R, right? Because it's clockwise. But now I will ask a question. And that question is the least priority group, is the least priority group pointing up? And if the answer to that is yes, that means you would have to invert it. Okay? So if your least priority group is pointing up, then whatever configuration you got in going from 1 to 2 to 3, you will have to invert it. That will be similar to saying that you are viewing the molecule from the bottom. If you look at the third molecule, I have here the highest priority at the aldehyde, followed by the CH2OH, followed by the C double bond C, and then of course the CH3. So basically we are counting 2 oxygens here. We are counting 1 oxygen here. This is a C double bond C, so you have 2 carbon-carbon bonds, and they are going to keep shuttling between carbons. On the other hand, in case of the isopropyl group, it will terminate in a hydrogen. So those are 2 different groups. And then again, going from in providing your priority order, past that, when you view the molecule, you will keep the least priority group away from you. So this is the direction you will view from. On the left, you have 1. On the right, you have 2. On top, you have 3. So in going 1 to 2 to 3, sounds like you're going the S way, and that will be your configuration. Sound good? Now, one sort of shorter method to do the same thing if you're not able to view molecules in certain directions, a shorthand is if in your tetrahedron you have your groups which are projecting. So let's say this is position 1, 2, and 3, and the 4th one is projecting out, right? So these 3 make sort of one face. But you can view the tetrahedron from whichever direction. So if you're viewing it in this direction such that your 4 is away from you, so looking at the priority order, you're going to go in 1 to 2 to 3. This is going to be your S. On the other hand, if you view from the right-hand side, then your 2 to 3 to 4, you're going to go in, let's change the color, you're going to go in the reverse order, and it will be position 1 which will be protruding out, right? So if your what protrudes out, sort of, if that group, in this case it was 4, if that is priority 2 or 4, an even number, then the configuration that you get is what you keep. On the other hand, if you're viewing from a direction such that the atom which is protruding out, which is out of the plane, is an odd number, so if it is 1 or 3, then you will have to invert it. So for example, in this case, in going from 2 to 3 to 4, you would have gotten an R, but that configuration of the molecule is supposed to be S. So odd numbers, invert it, even numbers, keep it. That's another way to view that. So I gave you two shorthands, sort of, if the lower or least priority is pointing up, get your configuration and going from 1 to 2 to 3 and then invert it. Another way of doing that is the group which projects out at the back. If that happens to be an odd number, then invert it. If it's even number, then keep it. All right. In the next couple slides, we are going to practice this so we can master it. So the question here is, draw a three-dimensional structure for each compound, put an asterisk on all the chiral centers. So 1-bromobutane, that's 1-bromobutane. Notice that's what you have. So do you think that this will have chirality center? Absolutely not. There is no R or S because there is no chirality center. On the other hand, if you look at 2-bromo-2-butanol, so let's maybe take a look at the, so here there is no chirality. And we are going to move to the next one. This should be 2 and this should be 3. Let's take a look at the next one. We have two molecules which have been drawn in a mirror-like fashion. So if you were to assign priority, you would say bromine has the highest priority, followed by the oxygen, followed by the ethyl group, followed by your methyl. So that's your 4. So if I were to view, that's step number 1 taken. If I were to view with the methyl, keeping that away from me and going from 1 to 2 to 3, looks like I'm moving in a anti-clockwise manner, right? So this must be S. On the other hand, if I do the same thing over here, priority order being the same, bromine is the highest, followed by OH, followed by the ethyl group, followed by the methyl. In going from 1 to 2 to 3, you are moving in an R manner. So notice, if your first original molecule turned out to be S, your enantiomer turns out to be R. Now, note that the clockwise, anti-clockwise that you get for R and S is just the way it is drawn. It's got nothing to do with the alpha rotation that you got for dextrorotatory and levorotatory. That was purely experimental. This is purely theoretical, the way it's drawn, okay? Also know that in this particular structure, if you would have viewed the molecule in from this direction, right, just the opposite direction like that, then that would have looked like R, because the methyl group, which is position number 3, which is an odd number, would have moved away from you. So you will have to invert it and give it S. So this is an S conformation. So one way to think about that is that either you place the molecule, keep the least priority group away from you, or you view it, you change your position, you view it, and then pay attention to what is the group which is projecting out. Is that, and is at the back. And so is that an odd number or an even number? And think about that, in which case you will have to invert it. Let's take a look at another one. I will have to fix these two again. Don't know why it does that. That's CH2, that is CH3. So we have over here again molecules that look like mirror images. It's 2-pentanol. Highest priority will be given to the OH, followed by the propyl group, followed by the methyl group, and hydrogen, of course, receives the least priority. So if you had to view, first of all, you will view in this direction. Hydrogen is away from you. In going from 1 to 2 to 3, this is the direction that you are viewing it in. It looks like this is going to be S. On the other hand, if you had to move in a direction where you have highest priority, followed by the propyl, followed by the CH3, you're moving in this direction, which is clockwise. That's going to be R. So in this video, we were able to talk about non-superimposable molecules, mirror images, which are not identical. And so we talked about what are called as enantiomers. What is the property of chirality? And so enantiomers are those compounds which will not have superimposable mirror images. That is the key thing. They are non-superimposable mirror images. In order to have that chiral center, you will need all sp3 carbon atoms. So 4 different groups, we talked about that too. It should not have a plane of symmetry, so no plane of symmetry. That's important. And those should be your optically active compounds. If you don't have that, if you have superimposable mirror images, identical mirror images, you're going to use the word achiral to describe that. We will, in the next video, talk about the meso compounds, the distereomers, and take this one step further.